rationalizing denominators and radical expressions. So let's say we're working on a problem that we want to simplify this radical expression, and we end up with a radical in the denominator. So we think we're at a fully simplified point. We get to, for example, 1 over the square root of 2. In math, it's poor practice to leave a radical in the denominator. So to get this thing fully simplified, we're going to have to implement some technique to get rid of that square root in the denominator, but still maintain the value of the expression. So what's important with this rationalization process is that we are not changing the values of our expressions, but rather just reformatting them. Our goal is to get rid of the radical piece in the denominator. So how do we do that? Well, if we know that we're trying to just change the format and not change its value, we're going to try to multiply by a form of 1. Because we know when multiplying by 1, 1 being the multiplicative identity, anything times 1 is itself. So the question, we don't literally want to multiply by 1 because I'll just get 1 over the square root of 2 again, but rather, again, a form of 1. So what is that going to look like? Well, we know some radical properties that are going to come in handy in this situation. If I multiply the bottom by, say, the square root of 2, knowing that these are both square roots in our radical properties, we're going to get the square root of 2 times 2, which is the square root of 2 squared. And we get a cancellation there, right? Because the square root of 2 squared, or the square root of 4, is just 2. So by multiplying the bottom by the square root of 2, I ended up with a simplified result of just 2, and now the radical is gone, which was my goal. But just multiplying the bottom by the square root of 2, and if I carry the numerator over, I would get an end result of 1/2. But that's not equivalent to 1 over the square root of 2. So by just multiplying the bottom by the square root of 2, I changed the value. I accomplished the goal of getting the radical out of the denominator, but we did not take into account that we want to maintain its value. We're just trying to reformat. So if I multiply the bottom by the square root of 2, I also need to multiply the top by the square root of 2. And now you see that this expression I'm multiplying by is equivalent to 1. I have something divided by itself. And our final result would be the square root of 2 over 2. This would be the simplified version, or the rationalized version, of 1 over the square root of 2. So let's look at another numeric example. Let's say we have 2 over the cube root of 3. We know we have to multiply by a form of 1 and not change the value. And we want to use the same radical through this multiplication process so that we can ultimately use those radical properties. So if I multiply by just the cube root of 3, which may be your first instinct, we're going to get the cube root of 3 squared, which is the cube root of 9. And the cube root of 9, I can't simplify any further. So that's not what I want to do here. But if I multiply by the cube root of 3 squared, then when I combine these two with our radical properties into 1 cube root, we get 3 times 3 squared, which is 3 cubed, or the cube root of 27, which is equal to just 3. And now that cube root is gone. So again, whatever we do to the bottom, we must also do to the top. And up top, we're going to get 2 cube roots of 9. And to make sure this thing's fully simplified, I would want to see if I can make a cancellation with this coefficient 2 and this denominator value of 3. There's no cancellation to be made. So this is indeed the most simplified format after the rationalization process of this original expression 2 over the cube root of 3. Let's take a look at a variable example. Let's say that we have x over the 4th root of x squared. Okay. So we identify a radical in the denominator. Actually, instead of x up top, I'm just going to put in number 1. So we know we have to multiply by a form of 1. We're going to use the same radical. The question is, I want to create a scenario that when I multiply these two radicals together, when I multiply the expressions underneath them, I get a perfect power of 4. So I don't want to just do x, because that's going to get me x cubed, and the 4th root of x cubed did not get rid of the radical because it can't be simplified any further. But if I do x squared, then when I multiply them together, I'm going to get x to the 4th underneath. And the fourth root of x to the fourth is just x. And now the radical is gone. And again, whatever I do to the bottom, I must do to the top. And there is your final result. So when might this pop up if it's not just explicitly thrown in our face? We might see something like this. First off, recall that rational exponents indicate a radical is involved. But what about that negative? Well, you know, when we see negative exponents, that's equivalent to the reciprocal of the base, so the reciprocal of x, raised to the positive version. And we know that 1/3 is a cube root. And we know radical properties we can split. And we know the cube root of 1 is just 1 in this case. So what we had at the beginning here is actually a scenario that does require a rationalization to ultimately get the most simplified version if we are required to get radical format. So like if the question's like, I want the answer in a radical format and fully simplified or rationalized. So we would have to manipulate this further in the event the question wants it in a radical format fully simplified. So I can convert it over to its radical format, which I have boxed off on the right, and then we would have to rationalize to get the thing fully simplified. So that's just an example to keep an eye out for. Just be aware that the rational exponents indicate there's a radical involved. If you have a negative there, know that that x to the 1/3 is present in the denominator. Another way you could think about this is not doing the reciprocal raised to the positive, but you can think of it as a numerator position, and just moving it down to the denominator changes the sign of the exponent. It's another way to think about the negative exponents. So now that we've seen some examples and when it might pop up, I'm going to do a combination of multiple terms. So let's say we have cube root of 2xy to the 5th z cubed. So let's say we have something like this and we want to rationalize it. So some people might say, well, from our strategies for simplification, we know that cube root of y to the 5th, that one piece, I could simplify further. And cube root of z to the 3rd, I could simplify further. But there's still going to be some radicals involved in the denominator because I can't simplify cube root of 2 or the cube root of x any further. So I might as well just wait to the end to get the full simplification after the rationalization process. So rationalization, we already know we're going to use the same radical because ultimately we want to use those radical properties, again, to sound like a broken record. But this time, instead of just having a single term underneath the radical, we actually have 4 terms. Now, you don't want to literally copy them over exactly with their exponents as well. You just want to copy over the base value. So we want to do a 2, an x, a y, and a z. Knowing that we ultimately are going to multiply what's underneath both of these radicals, and that's going to be resulting in us adding their exponents together, we want to make sure that the exponent values add up to a multiple of the index. That's the key to this rationalization process and what we're going to summarize at the end of the video. So we want to make sure exponent values add up, which is what we've been secretly doing this whole time, to a multiple of the index, and we'll see why that works out nicely. So for the 2's, they currently have exponents of 1. I can't manipulate the exponents in this. That's our original expression, but I can manipulate the exponents all I want over here. So if we have 1 and 1 currently, the sum of those is 2. 2 is not a multiple of 3. So I wouldn't want to leave exponent of 1 on the 2 to the right, but rather I want to put a 2 because 1 plus 2 is 3. I want to do the same thing with the x. With the y, I want to change that to a 1 so that I get 5 plus 1 is 6. And by the way, you might say, well, could I do negative 2 to bring it back down to 3? And the answer is yes, but incorporating negative exponents is going to be more of a pain, knowing that you ultimately have to multiply the top by the same thing and then you're going to have some more work to do at the end. So you want to stick with positive integer values for the exponents when you're using the rationalization process. Now the z can remain unchanged, so I don't have to do anything to it. I can just put 0 if I want. Now, when I multiply these together, we're going to get the cube root. So when we multiply these terms, we're going to add exponents. We're going to get 2 to the third, x to the third, y to the 6th, z to the third. And again, whatever we did to the bottom, we got to do to the top. I'm actually not going to write that z to the 0, but I wanted to originally, actually not, I'll just write it, to show that you should include all of the base values or all of the terms that are underneath the original. And we're going to do that to the top over here. So 2 to the 4th is 4, x squared, y, and z to the 0 power, anything to 0 is 1. So this is what our numerator looks like. Now look at our denominator. We still have that cube root, but taking the cube root of 2 to the third is just 2. Taking the cube root of x to the third is x. Taking the cube root of y to the 6th is y squared. And taking the cube root of z to the third is z. So our final result has a denominator of 2xy squared z, cube root of 4x squared y, and now I have an equivalent rational expression to the original that no longer has a radical in the denominator. So I successfully rationalized, and I know that's a valid equivalent version because I feel confident in the arithmetic execution, but also I multiplied the top and bottom by the same value, and therefore I was technically multiplying by a form of 1. So now that we have brought up how to rationalize, let's summarize. So first off, the goal is to eliminate radical from denominators So therefore, we are reformatting, not changing value of the expression. Okay, so super important before we get into the actual procedure. The goal is to eliminate the radicals from the denominator. So you don't care if they exist in the numerator. That is okay. So all we're doing is reformatting. We're not changing the value of the expression. So how do we do it? Step one, we need to use the same radical in our, I'll say same indexed radical in our form of, I'm going to put in parentheses 1, right? Because we're technically multiplying by form 1. So we copy over the same exact radical. We're at square root in the bottom, we got to use a square root in our form of 1. Cube root in the bottom, cube root in our form of 1. Then we want to make sure we copy over all the terms into our new form of 1. So copy over terms to put underneath the radicals. And then we can only manipulate the exponents in our form of 1, and we want to make sure the exponents add to a multiple of the index. That way, when you actually multiply the two radicals together, you're going to have to add the exponent values. And if they add up to a multiple, you'll get a perfect power of whatever the index is, and you'll get a clean simplification that should eliminate the radical. Now, when you're manipulating the exponents. You want to use non-zero integers. Or sorry, I should say non-negative, not non-zero. So what are the non-negative integers? We're talking about 0, 1, 2, 3, 4, and so on. Okay? So those are the values for the exponents you want to employ. And then again, we are multiplying by a form of 1. So whatever you do to the bottom, make sure you're doing to the top. So make sure to multiply the numerator by the same radical that the denominator is multiplied by. Once you've done that and you've successfully eliminated the radical from the denominator, always make sure to check for further simplification after the rationalization. So always check for further simplification after the rationalization. So let's end the video on one last example where we have to simplify this radical expression. So what you might do is simplify the numerator and the denominator individually if you can. So the numerator, the cube root of 8 is 2. The cube root of x is just cube root of x. I can't do anything with that. And the cube root of z to the third is z, so I can pull out a z. So we have this up top. And on the bottom, we have 2, and the fourth root of y I can't simplify, and the fourth root of z squared I can't simplify. So we're at this point. Now I can make a cancellation with these 2's. So now we have z cube root of x over fourth root of yz squared. And we already said we can't simplify that fourth root any further. And I can't combine that cube root up top and that fourth root on the bottom because they're different index radicals. So we've made some simplifications, and now we're at a point where we have this thing fully simplified when breaking down the numerator and denominator individually and even making cancellations when we had some. But is this fully simplified knowing that we have a radical in the denominator? And the answer is no. So now we have to get rid of that radical in the denominator to ensure that we have a fully simplified answer. So we're going to carry over that procedure that we just wrote down. We have to use the same radical, fourth root on the top and the bottom, knowing that we would need to multiply by a form of 1. We're going to use a y and a z underneath because the original denominator has a y and a z. And we need to make sure the exponents add up to a multiple of 4. And I want to just use non-negative integers. So I'm going to put a 3 because 1 plus 3 is 4. I'm going to put a 2 on that z. Whatever I do to the bottom, I've got to do to the top. Now on the bottom, we're going to get fourth root of y to the fourth, fourth root of z to the fourth. So on the bottom, we're just going to get yz, which is exactly what I want. And on the top, we're going to get z cube root of x fourth root of y cubed z squared. And this is what I'm talking about. Once you get to that final point, can you simplify any further? So yes, we completed the rationalization process, but upon rationalizing, we now have a z up top and on the bottom that can be canceled. And if you want to get really fancy, we could even combine these into the same radical, but we're going to have to change the index, which we've brought up in another video. But let's write down what we have. I'm going to actually write it off to the left. So we have cube root of x times fourth root of y to the third z squared all over y. And if we want to combine these radicals, we said that we could in a previous video change them over to their rational expression, or rational exponent version. And what we can do is get common denominators because we know the denominator indicates the index of the radical. It actually is a y down here, and I can simplify that with, actually, that's not worth our time because that's just going to put another radical in the denominator. So we're going to get these common denominators going to be 12, so 4 twelfths, y to the 9 twelfths, and z to the 6 twelfths. Again, this may be an unnecessary step, but it's kind of a good implementation of all the various rules and possibilities that we are allowed to do mathematically. So we're going to get the 12th root of x to the 4th, y to the 9th, z to the 6th, all over y. So we were able to combine everything up top into one single radical and leave the denominator radical free after the rationalization process. We made all the cancellations we were able to make. Each individual term underneath this 12th root can't be simplified any further because the index is greater than all of the exponent values. And that, I would say, is the most simplified version. And that is incorporating various simplification techniques and the rationalization process.